Hello, welcome back. The title of this lesson is called Square Roots with Perfect Squares, Part 1. So we have two main objectives I really want you to digest as we do this very important lesson, right? The first one is to really understand what a square root is and how to find square roots, in this case of numbers, but later on we're going to have square roots of variables, so this stuff is very important for future lessons. So number one, what is a square root? How to find square roots. The second thing, which is actually just as important, is I want you to understand that the square root that we're going to learn today is kind of the opposite function or opposite operation of the square. You know, when you raise something to the power of 2, we call it a square. So the square and the square root are kind of like opposites of each other. Peanut butter and jelly, they go together, sort of. Just like addition and subtraction are opposites, and multiplication and division are opposites, right? So now we know, or we will know, that the square, raising something to the power of 2, and the square root, those are opposite things too. Why do we care? Because when we solve equations very soon, we're going to use square roots to undo the squaring operation if we have one in the equation. So you know, when you solve equations, you always try to do the opposite thing. If you see addition, you do subtraction to undo it. If you see multiplication, you do division to undo it, and so on. Well, very soon, if we see a square in an equation, we're going to try to use a square root to undo it because it's the opposite thing. So, two things. What is a square root? How to find square roots. I guess that's sort of two things. And then the square and the square root are opposites of each other. So let's talk about this by taking our very, very first super simple problem. We have the number 4, and I ask you to find the square root. So you have this weird looking check mark thing. I recommend when you make your little check mark, you know, kind of your little square root symbol, go over here. Don't leave it like that. Put a hook at the end, which tells you where it ends. Because when you write these things really fast, it becomes hard to know, like, everything underneath it. You need to make sure that everything the square root is operating on is underneath the symbol. But if you don't put a hook at the end, sometimes you don't draw the lines long enough. So get in the habit of drawing these square root symbols with a little hook on the end, so everything underneath it is kind of underneath the square root symbol. All right, square root is very simple to understand, right? All you have to do is think to yourself, some number times itself gives you what is under that symbol. So we have the number 4. You have to ask yourself, okay, give me a number, but it has to be times itself to give me 4. So you could just kind of go through numbers, right, to guess in the beginning. 1 times, well, let's start with 0. 0 times 0 is 0, so that's not 4. 1 times 1, remember, it has to be times itself. 1 times 1 is 1. That is not equal to 4. But 2 times 2, that is the next number up, and 2 times 2 does equal 4. So without doing any work at all, we can say that the square root of 4 is equal to the number 2. And you would circle this guy as your answer. And the reason that this is the answer is because, I'll put BEC, because 2 times itself, that's what this means, 2 times itself is equal to 4. So every square root that you see, all you're trying to do is find out what number times itself can give you what's underneath the square root symbol. This square root of symbol, by the way, it's called a radical. So I'm going to kind of put this down here. This symbol, this is called a radical, right? So this, anytime you hear me say, look under the radical, what's underneath the radical? The radical is just that funny check mark. It looks like a square root symbol. It's all it is, right? Now, those of you who are paying close attention might realize that there's another answer to this, right? So we have the square root of 4, and we want to figure out something times itself is equal to 4. So 2 times 2 is 4, but there's another answer. Can you guess what it is? That other answer is, yes, we know that 2 times 2 is 4, but we also know that the number negative 2 times negative 2, see, negative times negative is positive, that's also equal to 4, which is what is under here. So really, for these radicals, for these square roots, there's really two answers. There's sort of the positive answer. The square root of 4 is 2, because 2 times 2 is 4, but there's a negative answer, because negative 2 times negative 2 is also equal to 4. Those are the only two answers that give you, when you multiply it by itself, what is underneath the radical. But in math, usually we focus on this positive answer. This positive answer here, the square root of 4 being equal to 2, this is called the principal square root. So when you take the square root of something and you look at the two possible answers and you look at the positive answer. The positive answer here, the number 2 here, is called the principal square root. We know in the back of our mind that there's another answer, that there's a negative number times itself. And technically that is an answer also. But here at this level of math, we don't worry about the other answer to the square root. So from here on out, I'm not going to talk about the other answer of the square root, that you can have a negative number there. We do talk a lot about that other answer when we get to a little bit higher math in algebra. It's not hard, it's just something we don't want to focus on here. We want to focus on the positive answer, the positive number that can be multiplied by itself to give you what's under here, and we call it the principal square root. So the square root of 4 is 2. This is what we write down. In the back of our mind, we know there's another answer, negative 2, but we're not concerned with that here. All right, now since this is the simplest square root we can have, I want to talk about a powerful way to find square roots. So this is very simple because it's a small number, but let's talk about what we call a factor tree. So we take a look at the square root of 4. You put a little 4 up there, put a radical symbol around it if you want to. Now what you do is you just ask yourself, come up with anything times itself, or anything times anything else to give you 4. And you can immediately recognize that the thing that pops in your mind is 2 times 2. So you put 2 times 2, put a little dot there. 2 times 2 is equal to 4. And we're drawing a tree like this because since we're doing a square root, notice the word square is in there. Remember, when we square a variable, it's to the power of 2. So the square root kind of involves the number 2, sort of. We'll talk about it a little bit more in a minute. But in this case, you take the number 4, you try to find things that multiply together to give you 4, and you're looking for pairs of numbers. And the reason you're looking for pairs of numbers is because this is a square root. And so you see I have a pair of 2's here, and I circle the pair, and every time I see a pair of numbers, I pull it out, and that is going to be the answer. So the square root of 4 is 2 because when we write a factor tree out, I look for pairs of numbers. When I see a pair, I pull, not both, I pull only one of the 2 that I have identified in the pair, and that is the answer. Now, for simple ones like square root of 4, you know the answer from your multiplication table. But if I give you the square root of 136 or square root of 249, you're going to have to use this factor tree. And we're going to do it. We're going to do it for these simple problems, and we're going to do it for the more complex problems here in just a minute. All right, let's move on to the next problem. Now that we've done all the talking here, let's take a look at the square root of 25. Notice I put a little hook here on my square root symbol, and my 25 fits nice and neatly tucked underneath. So all you really have to do is you ask yourself, okay, what number times itself gives us 25? And the answer has to be 5. 5 is the only answer that works. Why is 5 the answer? Well, the answer is 5 because 5 times itself, 5 times 5 is 25. The other numbers don't work. 4 times 4 is 16, that's not equal to this. 3 times 3 is 9, that's not what's under here. 6 times 6 is 36, and so on, that's not what's under there either. Now again, we know in the back of our mind that this is the principal square root, the positive number of the answer to this problem. But we know in the back of our mind that negative 5 times negative 5 is also positive 25. So technically, negative 5 is an answer to this too, but we're not dealing with that right now. We're not focused on that right now, so I'll kind of drop it. But just in the back of your mind, know when you get to higher math, we'll deal with those other answers. For now, we're just focused on the principal square root, which is the positive answer. So to do this guy using a factor tree, you just go over here and write, okay, square root of 25. And you just ask yourself, anything you want, something times something is equal to 25. The first thing that pops in your mind is 5 times 5 is equal to 25. Now these numbers, these 5s cannot be broken down any further. They're prime numbers. You could write them as 1 times 5, 1 times 5, but it's not going to get any simpler. 5 times 5 is as simple as you can get. You've identified a single pair because it's a square root. We're looking for pairs. We pull out one of these 2 guys as a pair, and so we say that the answer is 5, okay? And that's the final answer to that. Let's take a look at the square root of the number 1. So again, you ask yourself, what times itself can equal 1? And the answer to this has to be 1. Why? Because 1 times 1 is equal to 1. The answer has to be 1 because it is the number that when you multiply it by itself gives you what is under here. And in order to find this guy using a factor tree, you just write down the square root of 1 and you ask yourself what times what is 1. And you say, okay, 1 times 1 is 1. And this is a pair looking for pairs, and so the answer is 1. You pull out one of the two that you've identified as a pair, and the answer is 1, and you've kind of checked your work here. All right, let's move along. How many do I have here? Move along. Let's take a look at something a little larger. What about the square root of 49? Notice I have a hook at the end, so all of my numbers are cleanly underneath there. Now, from your multiplication tables, ask yourself what times what is equal to 49, right? What times what is equal to 49? And so you go through, okay, 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49, so the answer has to be 7. And the reason that this is the answer is because 7 times 7 is 49, which is what we have under here. Now, to find this guy using a factor tree, you just write 49, and ask yourself, okay, what times what is 49? The first thing that pops into my mind is 7 times 7, and I'm looking for pairs, and so the answer is 7. And so using a factor tree, you can quickly get the answer. Now, of course, for all of these, it's very simple to get the answer, but you're just going to have to trust me. In a minute, I'm going to give you some, or in a few lessons, I'll give you some that are very, very difficult without using a calculator or a factor tree. Let's find the square root of 9. Very common, right? Ask yourself, what times what is 9? Well, 2 times 2 is 4. That's not it. 4 times 4 is 16. That's not it. It has to be 3 because 3 times 3 is 9. And you can say this is because 3 times 3 is equal to 9. That's the reason. And if you wanted to use a factor tree, you could say, well, what times what is 9? 3 times 3. We're looking for pairs. And so the answer has to be 3. All right. Now let's take a look at our first problem that's, I think, a little more complex. I shouldn't say complex, but let's just take a look at it. We want to take a look at the square root of 16. Now ask yourself, what times itself can be 16? Well, 2 times 2 is 4, 3 times 3 is 9, but 4 times 4 is 16. So we're going to put that here. 4 times 4 is 16. Now let's go, and again, in the back of our mind, we know that that's the principal square root. Really, negative 4 times negative 4 is also 16, so that's kind of another answer, but we'll put that aside. We'll deal with that later, okay? Let's draw a factor tree for this. Let's draw the simple one first, and then we'll do one that's a little more complex. Let's say that we're trying to find the square root of 16, and you ask yourself, okay, what times what is 16? Most people will probably say 4 times 4 is 16. And you're looking for pairs. So you see the pair immediately right there. You circle the pair, and so the answer is equal to 4. Is that exactly what you predicted? Now let's take a slightly more complex factor tree, right? Let's do a more complex factor tree. Square root of 16. Give me something else times something else is equal to 16. Anything you want, okay? We know that 2 times 8 is 16. Now this is not a pair. We can't circle those. 2 can be further broken down to 1 times 2, but it doesn't serve any purpose because you'll just have a 1 and a 2 underneath again, over and over and over again. So we really can't break this down any further because if we keep doing it over and over, we'll just get 1 times 2. So we might as well stop here. 2 is a prime number, and prime numbers can't be broken down any further other than 1 times itself. But here we have 8, and 8 can be broken down into 2 times 4. Again, we have another 2. We can't break it down any further in a meaningful way, but 4 we can break down as 2 times 2. So we've broken down this number 16 as into a factor tree where everything on the bottom is a prime number. We've done this before in the past for other topics. I told you, learning factor trees would help us when we do square roots. Here we are, and you're not going to get away from it. We use it in algebra, we use it in calculus, we use it everywhere. So I'm showing you the real way to do this. Now you know the answer to this square root is 4. I'm just showing you what happens if you don't pick this. What if you choose a different set of numbers? Now everything in the bottom of the factor tree is hanging off on the bottom. You're still looking for pairs of numbers, right? So what you are identifying is that this is a pair of 2s, and these are both hanging off in the bottom, so you can circle those also. It's basically anything in the bottom of the tree, you're looking for pairs of numbers. You have a pair of 2s here and a pair of 2s here. Now what does that mean? What this means is you pull this 2 out. You can kind of just yank it out here. And I'll go I guess I'll go over here. This, remember, when you have a pair, you only pull one of the 2's out, and then you have another 2 from here, which you also pull out, but these are multiplied together. Because notice that in the bottom of the factor tree, everything is multiplied together to give you 16. 2 times 2 is 4. The 4 times 2 is 8, and this 8 times 2 is 16. So when you get to the bottom of the factor tree, everything on the bottom is multiplied together. That's what a factor tree does. It breaks down the number into prime numbers at the bottom that all can be multiplied together to give you this. So these are all multiplied together. Only pairs of number counts as singles, so the 2 comes out here, the 2 comes out here, but they're multiplied because everything was multiplied here in the end. And what do we get? 4. And this is the same answer that we got here. The reason I'm showing you this is because we're going to have to use factor trees for more complex complex problems later on. We have to. There's no way around it. And so we have to learn how to do this for the simple problems and the harder problems. If you identify 4 times 4 is 16, boom, the answer's right there. If you forget that and write down any other numbers that multiply and keep breaking it down, then you can pull these pairs out from the bottom of the tree, multiply anything that you pull out together, and you will get whatever the square root of this thing is. All right, let's take a look at the next problem. What about 64? Right, 64. We want to figure out what the square root of 64 is. Now, from your multiplication tables, you know 7 times 7 is 49, and 8 times 8 is 64. So you know the answer is 8, just from multiplication tables. But let's go and break it down in terms of factor trees and get some practice here. Now we know that we can I can go over here, I can say square root of 64. I can say, well, that's 8 times 8. Pull out a pair, boom, the answer is 8. Okay, but let's say we weren't that clever. Let's say we didn't recognize that. Let's put 64 right here. And let's pick literally anything else multiplied together to give you 64. You might be able to convince yourself that 2 times 32 is equal to 64. Now the 2 can't be broken down any further, but this can be written as 8 times 4, which is 32. Now the 8 can be written as 2 times 4 is 8, and the 4 can be written as 2 times 2 is 4, and this 4, don't forget this one's at the bottom of the tree also, it can be broken down as 2 times 2. So what we have to equal 64, the bottom of the tree is 2 times 2 times 2 times 2 times 2 times 2. All of that stuff equals 64. And so we look for pairs of numbers in the bottom. We see a pair of numbers right here. We see a pair of numbers right here. And this 2 is in the bottom of this branch, but this 2 is in the bottom of this branch, but still they're all can be paired up in the bottom branches. You see we have 3 pairs in the bottom. And so what we get is one of the 2's coming from here, one of the 2's coming from here, and one of the 2's coming from here. Remember, for every pair you see, you count them as only one number here. 2 times 2 is 4, 4 times 2 is 8. And this is exactly what we got when we just used our multiplication tables. 8 times 8 is 64. We broke it down into 8 times 8, that was a pair. And then we broke it down into prime numbers, and we get exactly the same answer either way. Here's our last problem, and then after that, I want to talk to you more about how square and square roots are opposites of each other. Let's take a look. Square root of 36. Now, from your multiplication tables, you know that 5 times 5 is 25. So you go up 1 from there. 6 times 6 is 36. So you know immediately the answer is 6 without doing any work. And then if you do the easiest factor tree you can think of, you go over here and do 36, and you say, okay, the thing that pops in my head is 6 times 6 is 36. So I write it down as 6 times 6. I'm looking for pairs. And so here it is. And so the answer is 6. Only a single 6 comes out. That matches what I found. Now let's go and do this guy. If we don't think of 6 times 6 is 36, let's think of 4 times 9 is 36. Because you can literally write a factor tree with anything times anything else. 4 times 9 is 36. The 4 can be written as 2 times 2. What can the 9 be written as? Well, 9 can be written as 3 times 3. Now, everything in the bottom of the tree is, again, prime numbers. Remember, a prime number can only be broken down into the number 1 times itself. So 2 can only be written as 1 times 2, so it's prime. 3 can only be written as 1 times 3, so it's also prime. So this factor tree is broken down fully, so the bottom of the tree is full of prime numbers. 2 times 2 times 3 times 3, this is 4 times 9, 36. So that everything in the bottom multiplies to give us 36. We now look for pairs. Here's a pair, and here's a pair. We pull out the numbers here. We have a single 2 from here, and we have a single 3 from here, and 2 times 3 is 6, and this is the answer to the square root, which is exactly what we got just by multiplication tables. So now we have conquered, at least with these simpler problems, how to find the square roots of perfect squares. Notice that the title said perfect squares. What does that mean? Perfect squares are problems that are easy because I know the square root of 36 is 6 because 6 times 6 is 36. I know that the square root of 64 is 8 because 8 times 8 is 64. But what if the question were, what is the square root of 65? How do you do that? Well, there is nothing times itself to give you 65. Well, you got to be careful. Yes, there is, of course. There's some decimal times itself to give you 65. But in terms of multiplication tables with the whole numbers, I don't know of anything that in my brain, like I can use a calculator, but I don't know a perfect number. That's why it's called a perfect square. All of these problems come out to whole numbers. But a lot of times, and most of the time actually, when you take a square root, you get an answer that's just a decimal or some non-perfect number. But in this lesson, we've only done perfect squares where the answer was just a whole number. Now what I want to do before we close the lesson is I want to drill this in your mind about how the square and the square root are opposites of each other. Really, it's called inverses of each other in math, but I'm going to call it opposites of each other. You know, when you add something, like if I add 3 to an equation or to anything, I can undo it by doing the opposite, subtracting 3. So I can add 3 and subtract 3 and immediately undo it, right? If I multiply by 5, but then immediately divide by 5, I've undone the multiplication. If I start with dividing by 6 and then multiply by 6, well, I've undone it. Why? Because multiplication and division are opposites. And addition and subtraction are also opposites. They help us solve equations. We've solved lots of equations by undoing things and getting the variable by itself. Now we're learning one more thing. The square, when you square something like 3 squared, 4 squared, 5 squared, 10 squared, square is very, very common in real life, right? So we have lots of equations with squares, and we can undo them with a square root. We can undo them with the square root. I'm going to say that one more time. You can undo a square with a square root, and you can also undo a square root with a square because they're opposites of each other. Let me show you how they're opposites of each other. All right? Let me give you an example. Let's say that I have 2 squared, and I'm going to wrap that in parentheses because I'm going to do the squaring first, and then I'm going to put a square root symbol around it. What is this? Well, if you think about it, you know, when we do order of operations, we haven't really told you yet, but the radical, the square root symbol kind of behaves as parentheses. It's on the outside. You have to go what's on the inside first and do it first. So when we have something like this, you do what's on the inside first. 2 squared, 2 times 2 is 4, and we still have to do that square root. But we already know what the square root of 4 is. We just wrote it down here. It's equal to 2. Do you notice how that we had 2 squared, and then we immediately did the opposite, which is the square root, and what happened? See, we squared something, and then we square rooted something, and the number on the inside actually was unchanged. Remember, I just told you we can add 3 and then immediately subtract 3, and it undoes the thing. Well, here, we squared it, but then we square rooted it, and so really what was inside is unchanged. Just like multiplying and then immediately dividing, squaring something, and then taking its square root, just they cancel each other, essentially is what happened. You can kind of think of the square root canceling with the square. And actually, that's a very, very good way to think about it. The square root can kind of cancel or annihilate a square. And so we can put the little slashes to indicate that, and the 2 is all that is left over. Let me write this a slightly different way. Let's say instead of this, I give you the square root of 4, right? And then I'm going to square it. So I have parentheses. I have to do what's on the inside first. So let me rewrite this again. Square root of 4 squared. Okay? Do that in a second. I'll show you why I'm doing that in a second. We have to go inside the parentheses. What is the square root of 4? We know the square root of 4 is 2, but we still have to apply the square in the outside. We do this first, get the 2, and then we have to square it. 2 times 2 is 4. And notice what happened. Here we had a 4. We took its square root, and then we squared the answer. We did the opposite thing, and what happened? The 4, which was on the inside, remained unchanged. It's like we did an operation to it called a square root, but then we did the opposite operation called the square, and because these things are opposite to each other, you can think of them as canceled. That's why I wrote it again here. The square can cancel with that square root, and the 4 is left behind. It is literally exactly like multiplying by something and then immediately dividing by it. If you multiply by 2 and divide by 2, nothing happens. The number that you had to begin with is just there, right? Adding 3 and subtracting 3, the number you start with is there. If I take 100 and then I add 3, I get 103, but then I subtract 3, I get back down to 100. The 100 I started with is just there. The adding and the subtraction annihilate each other, and they don't do anything. That's why these can be considered to be canceling each other, because when you square and square root, you kind of just go up and then down, back to where you started. When you square root and then square, you go down to a 2 and then up to a 4, and so it annihilates each other as well. I'm going to do this a couple more times because I want you to understand, but it's not very difficult, so let's just crank through it. Let's say, I guess I'll go down here, because we did the square root of 25. Let's say that we have the square root of 25, which we've already done, but then I apply a square to it. What is going to happen? Well, this square root of 25, you have to go on the inside first. You have to do the square root first. It's 5. But then we have to square it on the outside, and 5 times 5 is 25. Notice that the 25, which is on the inside, remains unchanged. And you can think of this square root canceling with the square, revealing and leaving behind only what is on the inside. Right? Similarly, what about 5 squared? And then I'm going to put that in parentheses, and then I'm going to take the square root. Let's try to think about it. The square that is here and the square root can be thought of as canceling each other, leaving behind only the 5. Why? Because if you go in here, 5 times 5 is 25. But then the square root of 25 is 5, so you go back to where you started from. The square and the square root are opposites of each other. I'll do just a couple more, and that'll be it. Let's say up here, let me do it in a different color to not confuse the problem statement. Let's say I have the square root of 49, and then I choose to square it. Well, the square root of 49 is 7, and then I still have to square it, and I'm going to get 49. I get back what I started with, and you can think of it as this square root canceling with the square, leaving behind what you started with. You can also think of 7 squared, and then applying the square root. 7 times 7 is 49. You still have to apply the square root. Square root of 49 is 7 because 7 times 7 is 49. You get back what you started with, and you can think of it as this radical canceling with the square, leaving behind only the 7. This is the very last one I will do. You can think of just how to cancel these things. 3 squared, and then take the square root. What's this going to be? You can think of the square root canceling with the square, leaving behind the 3. Why? Because 3 times 3 is 9, and then take the square root of that 9, and you get 3 back. And you can do a similar thing here. You can take the square root of 9, and then you can apply a square to it. You can think of this square on the outside canceling with this radical here, leaving behind a 9. And if you look at it, square root of 9 is 3, and you take this 3 and you square it and you get a 9. So I told you in the beginning that there were 2 main things I wanted you to understand, really 3. I want you to know what a square root is, I want you to know how to find square roots, and then I want you to understand how a square and a square root are opposites of each other and how they can be used to undo each other. In my opinion, in my experience, most students learn what a square root is, but they don't know what it's for because it's just not taught till later. It typically is why. But I think it's really important for you to know you're not just learning this stuff for no reason. There are lots of actual equations in real life that have squares in them. Gravity actually has a square in the equation. The force of gravity that we calculate to find out how much the moon and the earth attract each other, that has a square in there. What else? You know, the speed of light, E equals mc squared. It's got a square in there, right? I could go on and on. All the orbits of the planets have squares in there. The force of attraction between charge like electrons and protons, they have a square in that equation. Squares pop up all over the place in real life. And so when we're solving problems that involve those things, then we often have to get rid of the square to solve for something. And so we have to know what square roots are. So that was the point here. We also focused on this factor tree. And we basically said, hey, for all these problems, you know the answers. But really, this factor tree can be used to break down something like 16 into 4 times 4. You look for pairs, and then the answer is 4, right? And then if you didn't think of that, you can break down 16 into anything times anything else. Keep breaking it down to prime numbers. when you pull out what's on the bottom of the factor tree, multiply them, you're still going to get the same answer. And the reason I'm doing that is because I'm laying the groundwork, because pretty soon I'm going to give you problems that you will not be able to memorize, and you're going to have to use a factor tree to figure out the answers to the questions. So that's why we're doing it for easy problems, to kind of get you used to that so it's not so scary, right? What I'd like you to do is solve every single problem in this lesson, right? And then follow me on to part 2. We'll get a little more practice with square roots with perfect squares.